Hey everyone! You might saw in my previous video that I explained the temperature using a classical pendulum. While making this video, I realized that it maybe makes sense to define a mechanical temperature. In a system where no energy is lost, one could ask where the system is if I know its energy. So mechanical temperature could be on the one hand interesting for didactic purposes, but also raise new questions in nonlinear physics where I don't have an answer for yet, but maybe you have.
Hey Jack, I have a 1 kilogram ball that rolls in a normal parabola and has an energy of 14 joule. Do you know where on my parabola the ball is? I better know asked where you got this thing from, but how should I know, man? If you said 0 joule, I could tell you that it is on the floor. Can I also ask you yes-no questions about the section your ball is in? Sure, Jack. How much does Jack know about the location of the ball? The usual temperature is defined as the inverse of the partial derivative of entropy with respect to inner energy. If I have a coffee, then we talk about the entropy of the microstates in the coffee and its inner energy. Now I want to define the mechanical temperature analogously for mechanical systems. The entropy here is the entropy of location. How much does Jack know about the location of the blue ball? And the energy is the energy of the system, in our example 14 joule. The entropy tells us how many yes-no questions I have to ask to find out where the ball is. The differential entropy is a measure of how accurately I can determine where the ball is if I know its probability of location. The differential entropy H is given by the integral over the density rho from x times the logarithm of the density rho from x base 2. Assuming I have a residence density where the location is very clear, the entropy is low and also can be negative. If the location is more widely distributed, the entropy, in example the missing information of the location, becomes larger. To calculate the residence probability of the rolling ball, we first want to plot the distance along the parabola on the x-axis. For an energy of 8 joule, we get the following probability. Further up the parabola, the ball stops and the probability to find it here is the highest. For 14 joule, the ball rolls higher and there is a broader probability to find it. We can then insert this into the formula of differential entropy and got for 8 joule an entropy of 0.489 and for 14 joule an entropy of 1.632. So we can calculate the entropy for all energies and get the following energy-entropy curve. The slope at a point is now the derivative of the entropy with respect to the energy, just as for the temperature. The slope at each point defines the reciprocal of the mechanical temperature. Each parabolic ball system with a fixed energy can be assigned a temperature. If the energy increases, the temperature decreases and the entropy increases. Mechanical temperature tells how much less or more I know about the location of a system when I increase its energy. I was wondering if it's possible to calculate the mechanical temperature of a double pendulum. We are wondering how accurately we can determine the position of the lower sphere if we know the energy of the double pendulum. The problem is that the trajectory is chaotic. Same energies have different initial pendulum positions and different trajectories. Is it even possible to calculate a residence density that is unique for each energy? The problem is that the double pendulum would have to be ergodic to calculate such a thing. To see what a location density might look like, I ran the simulation over a grid and counted the time that the pendulum was in each pixel. Different colors show different times. The result is as follows. The colors show the time in seconds in logarithmic scale. In the middle pixel, the pendulum was 200 seconds. The graph shows the simulation of an energy of 11 joule and the other one for an energy of 8.3 joule. In addition, the initial position of the pendulum was plotted. We can then normalize this graph and insert this into the differential entropy formula. We get for each energy a location entropy H. We can see the information energy diagram for random initial positions of the pendulum. I wonder if the problem is solvable at all, and if indeed a residence density can be found that is the same for every initial position of the same energy.